In this video, we're going to learn about phase change. Now, phase change is a good opportunity to bring up equilibrium. Equilibrium is when substances will change from one form to another at equal rates. This can be in a chemical reaction or in a phase change. So, for example, consider water. Water, you may not look at it and notice that there is water vapor above the water, but there is. So if you have a bottle of water that is standing upright, um, let's say it's not entirely full, there's the surface of the water, you will notice that over time there will be particles sort of above the surface of the water. And this is because some amount of the water on the surface evaporates, and as it goes up, it eventually gets to the plastic container and then will condense there. And that's how it is that the particles seem to migrate up. But what this illustrates is that there's this equilibrium where particles come up into the gaseous phase and then go back down into the liquid phase. And at equilibrium, both of those are happening at the same rate. Um, the equilibrium favors there being liquid water. There's not a whole lot of gas, but there still is some. And there is, this is called vapor pressure. Um, if you change the temperature, that will change the equilibrium position. And that's why the vapor pressure at, say, 25 degrees Celsius is going to be greater than the vapor pressure at 20 degrees Celsius. And actually, you guys may have noticed if you've ever boiled water on a stove, you're going to see more water you're actually going to notice the vapor starting to be produced and starting to really show itself as you get closer to the boiling point. That's not because you've reached the point of full-on boiling. It means that there's just more vapor pressure as you bring the temperature to 60, 70, 80 degrees Celsius, even before you hit the boiling point. So in general, just as substances with high boiling points have strong intermolecular forces, substances with very low vapor pressure, where there aren't a whole lot of particles that exist in the gaseous phase over the surface of the liquid, they'll have quite strong intermolecular forces. If there's something that really has a lot of gas floating above it in the gaseous phase at some temperature, that means that there's weak intermolecular forces. So, for example, gasoline is something that is very volatile. You can smell gasoline. It's a liquid at room temperature, true, but you can smell it because there's a lot of vapor pressure above it. Gasoline has very weak intermolecular forces as a nonpolar molecule. And on the other hand, water has very strong intermolecular forces, so it has a very low vapor pressure. So the boiling point is where the vapor pressure has risen so much that the vapor pressure is the same as the atmospheric pressure. It just goes up and up and up and up and eventually reaches the atmospheric pressure. On a particulate level, on the level of the particles, when each particle's kinetic energy exceeds the energy of the intermolecular forces, a liquid will boil, or at least the particle will escape from the liquid as a gas. Now, when we look at this chart, we can see kinetic energy. As kinetic energy increases, you'll have this sort of hump of, where it is that the most molecules have a certain energy. So at a lower temperature, the average in this distribution, the average is somewhere near this peak. And that indicates that the average kinetic energy is about here, and this corresponds to some temperature. At a higher temperature, of course, that peak is shifted a little bit to the right, and so the average is higher, but also the distribution has broadened. And what this means is that there are fewer molecules that have exactly that average. That's why this peak is shorter. But you also have more particles with low and more particles with very high energy. And that's really important. You may be asking, why is it that there will be gaseous particles at 80 degrees Celsius when the boiling point of water is 100? Well, at 80 degrees Celsius, let's say we're looking at higher temperature here. At 80 degrees Celsius, the average may not have enough energy to escape as a gas, but there will be some molecules in this region that have sufficient energy to evaporate. This is our cutoff point. This is the energy. This is going to be your delta H for vaporization, meaning the energy required to cause evaporation to occur. And what we can see is that there are some molecules that have that energy. Moreover, when you compare the higher temperature distribution to the lower temperature distribution, it has lower vapor pressure. Of course, water is going to have lower vapor pressure at 20 degrees Celsius than 80. Well, notice that a smaller number of particles exist in this region of having enough energy to break free from the liquid. Um, so that is boiling point. As far as the energies involved in boiling, there's such a thing as a molar enthalpy of vaporization. That would be for boiling. This is just the heat released when when vaporization occurs. It's the heat absorbed when vaporization occurs. It is the heat released when gases condense into liquids. So gas to liquid, the Q for this, the energy of it, the Q is going to be, since we're going from a gas to a liquid, there will be bonds formed. Therefore, there will be energy released. So Q is negative. If liquid yields gas, Q is going to be positive, meaning when something boils, there will be an absorbance of heat. And that may seem counterintuitive to you, but what good way to look at this is that actually we sweat to cool ourselves. We sweat, we release water, and that water evaporates off of our skin. That is a physiological response to us getting overheated. And as the liquid sweat evaporates off our skin, energy is absorbed, and that actually has a cooling effect on us. If you have water on a pot to boil, you raise the temperature. It goes from 20 degrees to 30 to 40, 50, 60, 70, 80, 90 degrees. You're pouring energy into it, and it gets hotter. But once you hit 100 degrees, there's still energy going into it from the burner, and yet the temperature doesn't rise because the energy that's going into the particles is going towards breaking the intermolecular forces in the water. So energy is being absorbed. Molar enthalpy of fusion is another value, and the molar enthalpy of fusion is this is for solid to liquid, and the reverse being from liquid to solid. The values in both cases are the same, it's just different directions. But for solids going to a liquid, Q is going to be, solids to liquids, you are breaking IMFs, which means that, you're going to have a positive value, and liquid going to solid, Q is going to be negative. There's also sublimation and deposition, which would have values as well if that is something that we're measuring, that we're looking at. So, for example, dry ice is something that sublimes. Sublimation is, um, whoops, that is solid going straight to the gaseous phase. Sorry, solid yields gas. Deposition is when we have gas going to solid directly. So dry ice just evaporates straight from the solid phase, and could go in the opposite direction too. Um, and these, of course, have certain enthalpy values, but you really would have to be looking it up for the specific process. So you could be asked a problem like calculate the energy absorbed when 9.01 grams of water melts. So in that case, if we know that the heat of fusion for water is 6.02 kilojoules per mole, we could do this calculation. It also happens to be 334 joules per gram. And I'm giving both of these values in the same problem. It's easier to just go with 9.01 grams times 334 joules over 1 gram, and that's going to equal something. I'll get to that in a moment. If you only had the molar value, then you would have to say we have, H2O. O is with a molar mass of 16.00 grams per mole. And hydrogen is 2 times 1.01 grams per mole. And the total is going to be 18.02 grams per mole. We could say we have 9.01 grams of H2O times 1 mole over 18.02 grams, which changes us to moles. We're going to multiply this by 6.02 kilojoules per 1 mole. This is just the enthalpy of fusion, the enthalpy of fusion in kilojoules per mole. And whoops, my word, my stylus is being all sorts of weird today. Okay. And we would get to, well, this is 1/2, so we have 3.01 kilojoules will be the energy absorbed during melting of 9.01 grams of water. 3.01 kilojoules would be released if you were going in the opposite direction from liquid to freezing it into a solid. Finally, we have phase diagrams. I just want to show you an example of a phase diagram. Phase depends on two things. You're probably fully aware that temperature, of course, matters to phase. If something is like with water, water is a gas. If you heat it to 100 degrees Celsius and allow it to boil off, it is a liquid between 0 and 100 degrees Celsius. Below 0, it's a solid. But that is all assuming 1 atmosphere of pressure, exactly 1 atmosphere of pressure. If you change atmospheric pressure, you will change boiling point, which is why if you go into like the mountains, if you go to the Rocky Mountains where it's very high altitude, the atmospheric pressure is lower. They say the air is thinner because there's less oxygen per liter of volume. That will actually result in there being a lower boiling point. And that has a lot of effects. If you try to bake, for example, if you try to bake something, it's going to take longer to do, I believe, in the mountains than it would at sea level because atmospheric pressure is lower. And as a result, the boiling point will be lower. And so if you're trying to have some process occur in baking, it takes longer because the temperature at boiling will be lower. So just looking at this chart here, we can see it's not just temperature, but pressure that indicates phase. And solids exist at low temperatures, of course, but also if you have the temperature be low, you could still have something exist in the gaseous phase if the pressure is low. So notice this area where it says gas, you can have something at negative 78 degrees Celsius, whatever the substance is. We can have it exist at negative 78 degrees Celsius and still be in the gas phase if the pressure is less than 1 atmosphere. If the pressure is more than 1 atmosphere, it will be solid at negative 78 degrees Celsius. If we go to negative 56.7 degrees Celsius and 5.1 atmospheres of pressure, very specific conditions, if we go here, actually all three phases will exist at what is called equilibrium at this triple point. If you get a little bit, a little bit higher in pressure at pretty much the same temperature, you eliminate the gas from the equilibrium, and it's pretty much just solid and liquid at equilibrium. And you can keep reading this chart forever. There's a lot of data on here, but those are the important things that I'd like you to know. So I hope this video has been helpful to you. Let me know if you have any questions or comments in the comment section below. Thank you.